And we got another problem that might be interesting, but it doesn't look so. This problem is about finding maximum and minimum electric field, and the statement of the problem says that a uniform dielectric ball, that means non-conducting ball, that means solid sphere, has an electric charge Q uniformly distributed over the volume. The radius of the ball is R. A spherical cavity is made in the ball. Oh, Q is the total charge on the ball. And now a spherical cavity is made in the ball, and the surface of which touches the ball and passes through the center. Okay, so this may be the center of the ball, and this is the point where their surfaces touch. In this case, the ball is not additionally electrified. That means no more charges has been put over the ball, and some charges it lost. Find the ratio of the maximum and minimum electric field strength near the surface of the ball. Okay, so we can use the principle of superposition, and it can be argued that field strength of such a ball at any point can be found as the difference between the electric fields created by a solid ball and the electric field created by the charge that previously filled the spherical cavity. And what I'm trying to tell you that you can look at this picture and say this is the this is the solid ball, and this is a solid ball with a cavity, and cavity is like this. Yeah, this is the picture we have got, and this can be this. I can think of a solid ball, and sorry, it didn't work. A solid ball, yes, and minus the cavity. Yeah. So I'm trying to tell you that this configuration can be looked like this, and the electric field created by this ball at any point can be found as the difference between the field created by this solid ball at that point and minus the electric field created by this charge that previously filled the cavity. And it is given that the charge Q was distributed uniformly. Charge Q was distributed uniformly, and so that the missing charge due to after the spherical cavity has been created, we can find it like Q1, that will be equal to Q. What happened? Okay, so now I can write this charge within the cavity is Q1, and Q1 can be found out Q B1 upon B. B1 is the volume of the cavity, and B is the volume of the sphere itself, the ball, and so I can write Q as 4 by 3 phi, and its radius is R by 2. Yeah, so this is R by 2 cube divided by 4 by 3 pi r cube, and you will find it's get q by 8. And symmetry considerations suggest that the smallest electric field will be near the edge of the cavity, that is here, somewhere here, and the largest will be on the side opposite to it at this point. And if you wish, you can find the minimum electric field simply by writing 1 upon 4 pi epsilon naught q by r square minus q by 8 half square. And E max, the maximum electric field at the opposite side of the edge, we got the minimum electric field. You can write it will be 1 by 4 pi epsilon naught q by r square minus q by 8 3 by 2 square, 3 by 2 r square basically, not missing 3 by 2 r, and this is half r here. And get your results. Perhaps the answer is E max by E mean is equal to 17 by 9. And this is a good problem, though not interesting, but it's a good problem. Thank you very much for watching.